So in today's lecture, what we will go through is a categorization of the constraints. So we already, let's say, anticipated a little bit that theme. In fact, we already mentioned the difference between holonomic and non-holonomic constraints. So we said that for holonomic constraints, we had that they had this form. We have this, which is a vector of equations, written as Q, which is the vector of generalized coordinates, and typically T equal to 0. So where Q is equal, to Q1 to Qn transposed, where n is equal to what? To 6 if you are in space, times the number of bodies, okay? Okay, so this, in fact, could be further, let's say, divided into rheonomic and scleronomic, okay? So scleronomic holonomic constraints, scleronomic scleronomic is when basically there is no direct explicit dependence on time, okay, in the constraint equation. So time t does not appear explicitly in the equation. Otherwise, we have another categorization, which we call rheonomic. So let me write it. So it's rheonomic, which is the converse, okay, when t actually appears. So I'm talking about this dependence here. If it's explicit, we have a rheonomic, otherwise it's a scleronomic constraint. That's just a matter of categorization, okay? So time t does appear. Okay, so let's make an example, and then let's understand a little bit more. So let's have an example 1. Of a scleronomic. Okay. And to do so, let's take into account here. Okay, this image here. I hope you can see it. So here you have two bodies, I and J, so two bodies. Which are general, so we have two bodies in a system of bodies, which have a revolute joint, okay, in point P. So they are in 2D space. And there is what is called a revolute joint. So what is it, revolute joint in P, in point P? So it's basically a hinge, okay? Meaning that it allows the two bodies to rotate, okay, the one with respect to the other in P, but in P they are connected, okay? So it's a hinge. So the question now is, how do we enforce such a constraint that the body I and J should be connected through a hinge in P? So this is a hinge, as I was saying. Well, we have developed a way to do so, and it's the following. So we have to say we must enforce, we must make so that the position of point P, so this is the position vector of point P with respect to the body I, which we have already introduced, must be equal at all the times to the position of point P, but described in point, J. Okay? That's what we have to say. Is this clear? Because it's a revolute joint, so it must be said that when I describe the position of point P, taking into account the local frame of body I and J, the result must be the same, okay? So we know how to describe these two quantities here. And this means that Ri plus Ai applied over R0 I of the point P. And this is the description, the position of point P looked from the body I, must be equal to R J plus A R J P. Okay? So this is what we have to enforce. This is a hinge. In fact, this expression here is valid also in the 3D space, okay? Because this is a vector equation. Okay? So this is what we have to enforce. And now we know, because we have gone through the kinematics, how to express this. So if I write it explicitly, I have that, since I'm in the 2D space, this can be written as R1I, R2I, okay, which are the components of the position vector of the origin of the system I, plus what? Well, it's the rotation matrix in the 2D space, okay, for the body I. And this is a very simple one. We can call it as cosinus of theta I minus sinus of theta I, sinus of theta I plus cosinus of theta I, right? Like so. This is a 2x2 matrix. Applied over what? Well, applied over the components R01I over bar and R02I over bar. Okay, this must be equal to the other part. Sure, yeah, of course. Yeah, of course. Yeah, we know that rotational matrices typically are applied over quantities which live in the local frame. Yeah. And of course here just the same. So it's R1 and R2, but this time it's J plus the same thing. So it's cosinus of theta J in this case minus sinus of theta J, sinus of theta J cosinus of theta j applied over R0, 1 and R0, 2 j over bar. Okay, so that's our equation. As you can see, in this case, there is no explicit appearance of time, right? So these are two equations, yeah? And there is no explicit appearance of time, so that's why we call this a holonomic scleronomic constraint. Why holonomic? Because it has the form that we had before. So it means that it can be written, okay, as a combination of the generalized parameters q and not of its velocities, as it will be in the other case. And there is no explicit appearance of time. So that's pretty much it. So a very simple case. We can also have another case. Example 2. And for this, we can look at another picture. It's this one here. So this is the Canadarm2. So this is a robotic arm from the International Space Station. Okay. So as you can see, this robotic arm has an end effector here, which typically moves according to a law that you prescribe, that you enforce to the arm. Okay, you prescribe that this point here, this end effector, must move and rotate eventually in a prescribed way. Okay, so what kind of constraint is that? That's a constraint because you force the body, this part particularly, to move, okay, in a certain way. So it's a constraint. But what kind of constraint is that? So that's a rheonomic constraint. And why is that? Well, because if you think that, for example, this is point P, so this is our point P, and this is our body I, you have that your constraint is, so our constraint is position of point P with respect to body I, which is equal, as we said, as Ri plus AI applied over R0 Pi. Well, in this case, this must be equal to a certain law, F, which is a vector, which is a function of time. Okay? So in this case, the constraint has an explicit appearance of time, okay? Because you are prescribing a motion here. This F is a motion, okay? It means that you will eventually really force the components of the position vector of point P to follow a certain law of evolution with respect to time. So this is the first, okay? These are the two, let's say, the holonomic constraints that we have basically mentioned here, okay? So holonomic constraints, here we can, if you want, call it as one. And then we have another, the second category, which are called, as we have already mentioned, non-holonomic constraints. So non-holonomic constraints. and have the form A0, which is typically a function of Q and T, plus B, which is a matrix, times Q dot. So B is a matrix depending, of course, also on Q and T, which is applied over a vector Q dot equal to 0, where this is a vector nc times 1. This is a column vector, where nc is the number of constraints. So nc, number of constraints. While n is the number of the generalized parameters Q's, okay? And so this is what? This is going to be an nc times n, and this is an n times 1. Now, there is one very important thing to say. And that's that this is just not, this classification, this categorization of constraints is not just a matter of form, okay? So if they have one form, it's called holonomic. If they have another form, it's called non-holonomic. It's really a matter of a substantial differentiation. Why is that? Well, one could say the following. So we can write C, which is the vector of constraint, like this. And this is the holonomic case, okay? I derive with respect to time, okay? What do I get? Well, I get the following, no? I get the derivative of C, the vector. Remember that, you see, C has, let's say, it's a multiple dependence on Q and T, so that's why I'm actually using here the partial derivative on the Q, and then here I have the derivation of Q with respect to time, and that's a total derivative, plus derivation of C with respect to time. Okay, that's the total derivative, no? Equal to 0. But then what? Look, what if I call this B? This is our B. And this is our A. A0, sorry. So this could actually be written as B applied over Q dot plus A0 equal to 0, right? At this point, one could say, okay, so what's the point of all this classification? Because eventually, if I have a holonomic constraint, I can write it so that it has the shape of a non-holonomic one. We just demonstrated it. Well, that's true, but the converse, it is not. Okay, why is that? Because while the derivation operation is always, a granted possibility once we have the necessary requirements on the regularity of the function, so you can always derive. The converse is not always true. So the integral of a function, the existence of the integral of the primitive of a function is not granted. Okay, you know that. So I can always derive meaning that I can go from C, from C of Q and T equal to 0 to a 0 of Q and T plus B of Q and T applied over Q dot of T equal to 0. But the existence of the integral of a function is not generally granted, okay, assured, okay, meaning that from here well, it's not granted, typically, that I can come back here. So sometimes I can, of course, but not always. What do I mean that sometimes I can? That, of course, if I start from here, okay, if I start from here, and then I arrive here, of course I can come back. Why? Well, because this is where I started from, so I'm sure that the integral function does exist, you know? But in principle, I do not know, okay? If I start from this point and not from here, I'm not sure that, you know, that I can integrate and find the integral of the function. Is this clear? Okay. This is a very important classification, and today we'll try to see why it's so relevant, because this will, you know, somehow really influence deeply the formulation of the equations of motion, you know, for these two kinds of constraints. So this is not always possible. Okay. Okay, here I can always derive a given appropriate regularity conditions. So, but these are typically generally fulfilled. To clarify a little bit, okay, this kind of relation that exists between holonomic and non-holonomic constraint, we can also, typically it is done in the literature, distinguish between constraints which are called geometric and kinematic. Okay? So, while the holonomic let's say versus non-holonomic constraint so the holonomic versus non-holonomic constraint categorization is a substantial one. There exists another one, which is actually just a matter of shape, really, only of mathematical expression of the form. which is, again, as I was mentioning, the differentiation between geometric and kinematic constraints. So I would call it only a formal one. Which is the geometric versus kinematic. Okay, so here we have holonomic and non-holonomic, and then we have geometric and kinematic. So what's the relationship between the two? So we have geometric so have the form C Q T equal to 0. 2 kinematic they have the form typically, well, you can write it like, let's keep it as we did. Well, one then could say, okay, but what's the difference then between geometric, kinematic, and holonomic and non-holonomic? That non-holonomic can be defined as what? Kinematic non-integrable constraints. Okay? What does it mean, non-integrable? Meaning that I start from here, but I cannot go back here. Those are the non-holonomic constraints. Okay? The holonomic constraints are the geometric, of course, plus the kinematic integrable. Okay, so those that have this shape, but can actually go back here. They can be re-expressed like here, because the integral does exist. Okay, so this is just a matter of, terminology, but it's important because eventually then, in the future, you will see this, differentiation, and you have to know what is the categorization between them. So we can write holonomic they are geometric and kinematic integrable. Okay? While on the other hand, we have non-holonomic, and they are just the kinematic non-integrable. So you cannot go back to the other shape. Why is all this? Why is all this differentiation? As I was mentioning before, there will be a substantial difference and effect in the formulation. Let's make an example of non-holonomic constraint. And let's also look at some tricky aspects that can arise. All right. Let's see, for example, okay, let's use this picture here. So this is what is called a spinning top. Okay. In italiano una trottola. Okay. So when you enforce a condition, a constraint on that, for example, saying that it has to rotate with a certain velocity, okay? And that, when I mean velocity, in this case, angular velocity, I mean it from a vectorial point of view, okay? Meaning that it has to rotate with a certain speed, but also with a certain direction, inverse orientation, okay? So I want to enforce a condition on the spin, if you want, spinning velocity of the spinning top. Okay? How do I do that? Well, we have seen that the angular velocity can be written like that. It's omega I, right? That's the angular velocity. We have seen it. In fact, we can also, in the dual representation that we introduce, I can directly use the one expressed in the local frame of the spinning top. And we saw that if I use Euler's parameters, this can be written in the following way: 2hi times theta dot I, okay? Which could also be written as G over bar I applied over theta dot I, where theta dot, of course, is the vector. Theta I is the following vector: is 0, 1, 2, and 3 I. For Euler's parameters. Well, what do I enforce? I want that omega, which is again G I theta dot I, must be equal to a certain f of t, function, vector function of t. Actually, let's say that this f, in general, could also be a function of the generalized parameters. So if you look at this, what do you have? You have that your q dot is what we call theta dot here, okay? Because the condition in this case is only on the rotation, it's not on the position R1, R2, R3. So you can think about this q, with R1, R2, R3 like this, okay? So this is one. Then you have that B, our matrix B is what we here call G over bar, okay? And our A0, I, is nothing different than Q, our Fi. Here we can call it like this. So you see that if you do this, this will assume the form. So it becomes actually, this you can call it this minus F0, just to have it exactly the same as we did before, and like this, right? So typically, non-holonomic constraints are those which involve rotations, okay? Conditions enforced on the rotations. One additional point that I would like to discuss with you is the following. So one could say, okay, when I impose holonomic constraints, it means that I'm actually defining something directly in terms of the generalized coordinates q. So I'm forcing directly the values of q. While with non-holonomic constraint, typically I enforce condition on the velocities. Okay. So on one case, I actually impose a condition on the actual values, okay, of the variables q. While with non-holonomic ones, I impose a condition on the variation over time, okay, of this velocity. Is it the same? What is in the count of the constraints? Do actually holonomic and non-holonomic constraints count the same in terms of enforcing constraints? And then in the Grubler count that we have also mentioned last time, do they actually have the same value? Do they, when I have to say, okay, I have n generalized coordinates and then I have nc constraints, do I have to discriminate between holonomic constraints and non-holonomic ones if one actually enforces something on the actual value of the q's while the other on their variation? Do they count the same? That's the point. We'll see that they actually do, of course, but that's a tricky thing to see. So let's go a little bit deeper onto that. So the question is, so holonomic constraints enforce conditions on directly on the q's. Okay, let's say on the q's, while non-holonomic ones on their variation on time. Okay, now the question is, do they count, okay, do they count the same in terms of reducing the number of, okay, in reducing the number of parameters of parameters q, which we can define freely So that's the question, okay? Because one, as I was saying, influences and dictates exactly the values. The other one, the velocity, so the change in time. Okay, how do this work? Let's have an example on that, which clarifies hopefully the question. Is it clear the question that I'm posing? One acts on velocity, the other one on the actual generalized coordinates. So do they actually count the same in terms of Grubler count? Oops. So here we have this case. So this case is a case of a coin, okay, tossed over the floor. This is a coin which is just moving over the floor. And the requirement is that the motion of the coin while it rolls over the floor happen without sliding, okay? So there is just pure rolling without sliding. coin tossed over the floor. So without sliding. Okay. How do we enforce that, okay, in terms of conditions? Let's see. So we will try to enforce two things. Okay, so P is the contact point, okay, here. So this is the contact point. The contact point between the coin and the floor. Okay, so it means that if we want this to happen, this rolling without sliding thing to actually be enforced, it means that here at point P there is to be no relative motion. Okay, between the floor and the coin. How would you enforce that? Could you guess? Anyone from home as well? Just try to guess. It's not that hard, in fact. It's a simple way. You have to describe that point P does not have to move with respect to the floor. This is what you have to enforce, right? It has to roll without sliding. Just try. I mean, nobody's here to, to judge you. Yeah, that's the complex way of saying that. But in terms of the mathematical, expression that we have seen, how could you say that in a much simpler way? In fact, remember maybe that we can, and we have developed it for that reason. We can express the velocity of point P. Even we have two ways of describing the velocity and the motion of point P. One is with respect to the inertial frame, and the other one is with respect to the local frame. So it means that if I see it from the inertial frame, point P, when it touches the ground, or it touches the floor, is it moving or not? No, right? So it is still, because it is actually instant by instant in contact with the floor. So it has to be attached to the floor. And if it's attached to the floor, what's its velocity in the inertial frame? 0, right? So this means that we can write the following. That P, the position vector of point P, of the vector of the point P, sorry, dot must be equal to 0. But this we know how to write it. So let's say that we are here using the triad of angles, so Euler's angles, to describe the orientation, okay, of the coin. So we say that we make use of the Euler's angles phi, c, and theta about B1, B2, and B3. Okay? So this means that phi, psi, and theta are the three angles which we Euler's angle that we use to describe the orientation, okay, of the coin. In the drawing here, I hope it's clear, but so phi here. This is the angle between, basically, you can say V2 and the vertical from on the ground. Okay. So this is one. Theta here instead is the angle between it's the angle about, you see, it's the first one here. Sorry, it's the last one here. So it's the one about B3, okay, phi. And so you can define it as the angle between the contact point and the direction defined by the axis B2. Okay? This is phi, the first one. Okay, the last one is theta. Yes, that's actually, sì, allora, questo qui in realtà, so I go in English as well. So this one is, let's say, another way of calling it, it's var phi. So it's kind of italics, è un, come si chiama, corsivo, okay? That's the same letter. Exactly, okay? So if you want, yeah, you can call it theta or you can call it var phi, okay, which means capital or italics, okay? But it's just a matter of understanding each other, okay? So the important thing is that we have to enforce two things. First, that the coin is touching the ground, okay? It has to be in contact with the floor. How do we do this? So first, oops. Enforce that the coin touches the ground. How can we do that? We can say, for example, that R3, which is the vertical component of the vector which goes from O to O prime, must be equal to what? If A is the radius, okay? So let's write it here. So A is the radius of the coin. I would write that A multiplied by the cosinus of phi, of the first one, must be equal to R3, right? That's a projection if you want. Is this clear? So I have it here if you want. Let me just, so this I can prolong like this, okay? That's the vertical. What I want is that this part here, it's equal to R3. That's R3, right? Because you can call it like this if you want. This is our R3. Oops, sorry guys. This is our R vector, okay? That's the one connecting the inertial and the local one. So I want the vertical component of this vector, which is typically R3. So if I want to say that point P must be on the ground, I have to say that the third component of R must be equal to what? To the radius of the coin multiplied by the cosinus of this angle here, okay? which is exactly phi. Okay, so if phi was 0, it would mean that the coin would be perfectly orthogonal to the ground. Okay, and in this case, R3 would be equal to what? To the cosinus of 0, which is 1. So R3 would be equal to A, the radius, exactly. Okay, do you see that? So this is the first way of enforcing it. We say that R3 is equal to to A times the cosinus of phi. Okay, that's the first condition. The second condition is that there has to be no sliding, rolling without sliding. So 1, and then 2. Rolling with no sliding. And we said that this can be said by imposing that the position point P, actually the velocity of point P, is equal to 0. But the velocity of point P can be written like so. R dot plus A, that's the matrix, or acting over omega bar times R0P is equal to 0, okay? Where R0P, this is the vector that basically connects O prime to P, if you want. Is it clear? That's one way which we have already used. And this has to be equal to 0. So that's the second condition. Now, we saw that omega is basically, as we said, is G applied over, this is theta, with what G being equal to the following. You can actually derive it, but I will spare you. See? And 0. And then we have the sinus of psi 0, 1. If you try to get G, that's what you get. Okay. Of course, we have the theta, in this case is phi, psi, and bar phi. I suppose this is what we already have seen. Or if you want with the dot, it's like that. Okay. And RP, R0P. What is it, R0P? So R0P over bar, sorry, is the vector with which I said connects O prime, which is the origin of the local frame, to the point of contact. Okay, how can we describe it? But it has to be expressed in the local frame, in B1, B2, B3. So if you look at, oops, this picture here, O prime P, I would use, okay, bar phi, okay, this one. I would use this angle here, because this is the angle of the spin about B3. What's the projection? Well, if you do the count, if you take that picture on your mind, that's minus a sinus of phi minus a cosinus of, var phi, 0, right? This is in the local frame. Does it make sense? Yes, because it has 0 component along the third axis, because the third axis B3 is normal to the coin. Okay, so the contact point, of course, has to be on the surface of the coin. So that's why it has no normal component. And then what? Let's take a look. Well, if you imagine that initially, as I said, the cone stays like this, and this is basically B1, and this is B2, and B3 is coming outside, okay, from the board. This is P, okay? So the vector O prime P, in terms of, in the frame B1, B2, B3, has the component 0 minus A, 0, right? Is it okay? Does it goes to the right result? Yes. Okay, so that's our parameterization. And now we can express, easily our condition. The condition P dot equal to 0 becomes well, we said that R0 plus A acting over omega divided over R0 P over bar 0, and therefore we can write, for example, that R dot is equal, of course, to minus A applied over omega vector R0P. And if we take into account all the descriptions that we have already gone through, this results in the following. R1 dot, if we write it in componential form, R3 A, which is the radius. If you do all the math, you get the following. Var phi dot cosinus of psi. Then you have psi dot sinus of psi plus var phi dot sinus of phi sinus of psi. And then we have minus psi dot cosinus of psi minus phi cosinus of phi sinus of psi. You see, that's our condition written in componential forms. Now, if I imagine to multiply, okay, let's write it like this. I can rewrite. So if I want to rewrite it in a simpler way, zero sinus of psi minus cosinus of psi 0, 0, 0. cosinus of psi, sinus of phi, sinus of psi, minus cosinus of phi, sinus of psi. This multiplies what? Multiplies phi dot, psi dot, and bar phi dot. Okay? Now, why do I, so this is a, you see, this is a non-holonomic constraint, what we eventually wanted to see. And as you can see, you are imposing a condition on the time variation of the variables. Okay. If you want, you can also rewrite it in the following way. So if you, let's say, if I multiply times or by delta t or dt, both sides, I get the following. I get what? I get dr1, dr2, and dr3 being equal to what? Well, to the same, of course, matrix, which I briefly rewrite here. Times, of course, in this case, delta of the angles. Okay, so you see the variation of the parameters do influence the variation of the position R1, R2, R3. So I'm imposing, yep. Dovrebbe essere da dimensionale? Perché da una parte è dimensionale, dall'altra è dimensionale. True, because I forgot an A. Yeah, no, correct. Correct, thanks. So there is an A, of course, here. We missed it. Yeah, thanks. So you see I'm imposing a condition on the variation, while if you look at the first one, the very first that we imposed, this one here, the one where we said that the coin has to be in contact with the floor, we directly conditioned the values of the variables. So here, phi directly was related to R3. Okay, so this is a holonomic constraint. The other one is a non-holonomic constraint. But so the question which we wanted to answer at the beginning was, okay, this is all interesting, but what's the point? The point is that now I have one constraint, which is this one here. And then I have 3. So here we can write. So direct condition on the Q's, okay? While here, the point is that this is condition, oops, on the variation of Q's. Okay, but so Did you remember what we did with the Poisson mechanism? Okay, we said, okay, there are 27 parameters, then we have 26 linearly independent conditions, and then we eventually were left with only one parameter, which could be defined independently, okay, freely, arbitrarily. How about that? Because I saw that in the first one, the holonomic one, it's actually similar to what we are accustomed to see, okay? Condition between pointwise values of the variables. But here we have a condition on the variation. So in the Grubler count, how do we do this? How do we count this condition here, the last one? So the question is, we have 6 parameters, right? Generalized parameters. Okay, which is R1, R2, this is, and then we have phi, C, var phi. And how many conditions? We have seen it. Holonomic plus non-holonomic. 4. No? Let's call it constraint. So it would appear that only two parameters can be set arbitrarily. Huh? Is this true? Well, if you think about it, this is the case. Why? Because it is true that these three conditions only enforce a condition on the variations. But once you establish an initial condition, initial value of R1, R2, and R3, okay, well, if you have the initial and then you impose a condition on the variation, it's actually equal to, conditioning the actual values of the variables, correct? So in this sense, holonomic and non-holonomic constraints they count equally in the Grubler's count. This one that we have done here, given that there is an initial condition. Okay, and this is something that you have already seen when you have to solve differential equation systems. You need an initial condition to be able to solve the system. So the answer is yes. Yes. But given that also an initial condition to close the problem. Okay. Once I know where I start, if I impose condition on the evolution of the variables, it's just basically equivalent to saying to condition exactly the variables themselves. Okay. Is this clear? Questions from home? Okay. Now this is let's say the last concept that I wanted to present today, and it relates exactly on what we have seen today. So that's called the coordinate partitioning. So we have said already that when you enforce a certain numbers of constraints, you basically establish, this is equal to establishing a relationship between the parameters describing the system, okay? In fact, those that can be arbitrarily set, they are called independent parameters. And those can instead basically comes from the arbitrary defined parameters are called dependent parameters, okay? And this is always true, okay? So once we set constraints, so NC constraints equations on a system of, let's say, NB bodies in 3D space, we can always define what? Well, we have NC dependent generalized parameters, or coordinates if you want, which we can call as QD, which is a vector NC times 1. So this is the first one, and then what? Well, something around N minus NC independent which we call QI with a lower subscript. And please do not confuse this with the superscript I, which defines the body number. Where N is equal to 6 again times NB. So you can always do this partitioning. But now the theory that we will develop instead only works for holonomic constraints. Okay? So this, please keep in mind this if I can write, so this is a priori, okay? So this holds for holonomic and non-holonomic constraints. For all constraints. Okay, this partitioning, this differentiation between independent and dependent. But if I can write the constraint as C, meaning I'm talking about non-holonomic, constraints. So this is a very important if. If I consider the following. I then consider a virtual motion, virtual displacement of the system. What does it mean, virtual? Virtual displacement. You already have seen it so many times that, okay. So virtual. It's infinitesimally small. So it's infinitesimal. So it's very small. And it's compliant with the constraints okay. What does it mean? If this is true, that it's compliant with the constraint, what does it mean? So it means that I can do the following consideration. So before the motion, for the virtual motion, I had that the constraint could be written in the following way. I could write it C0 equal to Q0 and T. This is equal to 0. And then, so after the virtual motion, well, I'm in another state, okay, which is very close to the initial one, which I can call C1 of Q1 and T. But since this Q1, okay, which are slightly different from Q, okay, must be compliant with the constraints, also this constraint must be enforced, okay? They must hold, okay? So that basically we could write delta Q as Q1 minus Q0, okay? That's this small delta here. And we can call delta C as C1 minus C0, okay? It's just strings from the definition of virtual displacement. So we therefore have what? That delta C is equal to 0, right? Please keep in mind that all that we are writing here is based on that big if. So it means that we are writing this only for holonomic constraints, okay? If I derive this equation, I can write the following. Okay? I define this CQ, this matrix, as exactly this dc over dq, okay? And this is the system Jacobian. This is called the Jacobian of the system. Okay. And it's written like this. it has this structure. It's a matrix which has n columns and nc rows. Okay, so each row basically is a constraint. Okay. So this is an nc times n matrix. So this matrix, if the constraints are linearly independent, has a full row rank. So this matrix has a full row rank, which is equal to 1c, if the nc constraints equations are linearly independent. Okay, this is obvious. So the last passage is the following, and then we're done. I define the following partition. So I say that my Q is basically divided into a subset of Qi and then another set of Qd, where Qi are the how many? N minus nc independent coordinates. Independent coordinates. And Qd are the nc dependent coordinates. Okay, I just do this. I can rewrite the dc equal to 0 as, sorry, as CQ applied over delta Q, okay? But this can also be written if I do insert the partitioning within Q as C QI applied over the delta QI plus C Q dependent over delta Q dependent equal to 0. Okay? And since this is an n minus nc vector, okay, times 1. This is, of course, what? An n c n minus nc times n minus nc matrix. This instead is an nc times nc, and this is nc times 1 vector. So, since we are taking into account the fact that we have all linearly independent equations, we can choose this CQD, which is a submatrix of CQ, in a particular way, and then we're done. So CQi and CQd are submatrices of the Jacobian. CQ. If we have NC linearly independent equations, we can choose CQD, which is NC times NC, as a non-singular matrix, okay? Because we said that the Jacobian, in case of NC linearly independent equation, is as a full row rank. So we can select the CQD, which is as NC times NC matrix, to be non-singular, okay? Is this clear? Okay, non-singular matrix. Why is this important? Because we can invert it. Okay? And so we can write the following: from CQi over delta Qi plus CQd applied over delta Qd equal to 0, we can reverse this and write delta Qd equal to minus CQd to the minus 1, which we can invert because it's non-singular, applied over CQi applied over delta Qi. Huh? We can call this as CDI, huh? It's a matrix. And therefore, we have a relationship between the dependent and the independent matrices. Okay, that's you see, this is a super nice expression that allow me, you see, to express the dependent coordinates directly in terms of the independent one, meaning that with the constraint equation, I can set the independent values, Qi's, and get directly the dependent ones. And this is very, very nice because you can imagine that when I will write the equations of motion, I can directly do this substitution, and this will simplify a lot the formulation of my equations of motion. Okay, but this can only be done for holonomic constraints. Okay. Last but not least, the Qi, as I was mentioning, which are the independent parameters, are also called degrees of freedom of the system. Okay. So they are called degrees of freedom also called DOF with a small s when they are plural. Okay. So when you hear this term, it means that we are talking about the the parameters the generalized parameters which can be set arbitrarily. Okay? So we're done. Sorry if we went a little bit long, but we started a little bit later because of the previous professor.